I couldn't get in my office today. I was going to make another copy of Sean's, but we'll just look at a couple of them, and I'll get you a copy later. Of course, there's some in the book. This particular section is 510. So we're talking about improper integrals. And you're like, well, what the hell is an improper integral? I'll just look at a particular function to show the two kinds of improper integrals I can have. So this is 5.10. Remember, we are not doing 5.8. 5.8 is just a bunch of formulas of how to integrate. And so since I've taught you how to integrate with all those methods, I'm not going to do the one where all you do is fill in a formula. So improper integrals. So 1 over x is the perfect version of it. And of course, you can imagine it's pretty hard to get the area underneath. But that's what we're talking about. We're talking about finding the area underneath this curve where obviously there's two issues, right? We've got, right, the limit as x goes to infinity of 1 over x is kind of questionable, right? Kind of questionable. We don't necessarily, well, we know the limit is 0, right? So, but how do we find the area in that case, right? How do I keep adding up all that area is the problem. And of course, the limit as x goes to 0 from the right of 1 over x is positive infinity, right? So, but these are our two cases of improper integrals. If I have an integral where my function goes off to infinity, right, as x goes to infinity, or if my function goes to infinity as x goes to a number. These are my two cases. And if you look at the textbook, of course they say it, they kind of say it the same way. Where are they saying it? It's in there. This particular box is saying it. It's saying if I have an integral going to infinity, we want to test if it's convergent or divergent, right? And same thing if I have just a place where the function is unbounded. It's in here. It's just worded horribly. But the process here is what I want us to take a look at. So imagine I have these two integrals, let's say from 0 to 1 of 1 over x, right? So the problem here is at 0. Yes, you agree? So we want to rename, we want to say limit as a goes to 0 of the integral from a to 1 of 1 over x dx. So we're going to take that piece that's trouble and put it in as a variable, finish the limit as always, and then evaluate the limit to see if I actually get a sum, the area, or if I get something that's divergent. Same thing with this one. As I build my integral from let's say 1 to infinity of 1 over x, right? I want to replace that infinity with a letter and look at the limit as a goes to, right, that letter goes to infinity of 1 over x. So we know this antiderivative, right? ln, right? And so this is ln of 1 minus ln of a, right? This is ln of a minus ln of 1, yes? So ln of 1 is 0, right? But of course, what I forgot is I have a limit on each of these, sorry. So what happens to a as a goes to 0? Look at my ln function. It goes to minus infinity, right? So that one's divergent. And what about this one? Where's ln going as a goes to infinity? Infinity, divergent. Both of these are divergent. Say again? Exactly. If I don't get a number, it's divergent. If I get a number, convergent. So I found an area, right? Okay. So notation is pretty clear. When I can use it, it's pretty clear. Graph the function if you're in doubt, right? Graph the function, and you should see either the function going off to infinity or right, the function going left or right to infinity. I need a trick, one particular trick that I need is I need to remember if I have any base like x, that I can rewrite that as e to the ln of x. So for example, sine of x is e to the ln of sine of x. Okay, so any base I can write as e to the ln of that base. And you'll see where this trick comes into play in a minute. Let me just find my improper integrals. Okay, here we go. First problem. I've got the integral from 0 to 3 of 1 over square roots of 9 minus x squared dx. Now, and what antiderivative do you recognize here? Arc sine, yeah. We definitely see an arc sine here. I want to take a look at the picture because certainly I know when I plug in a 3, I get 1 divided by 0, right? So I know the issue is at 3, but I'd still like to be able to see it. So y equals 1 divided by square root of 9 minus x squared. You know, and when I'm doing something on Desmos, you probably want to be doing it on there as well. So I'm going to 0 to 3. It's pretty clear that the function goes to infinity at 3, right? But I'm wondering if that area is finite. Even though it looks like it goes off to infinity, it certainly gets really close to 3 really quick. So maybe this is a finite area. Maybe this thing converges. So I can already tell I'm going to need to take the limit as x goes to 3 of the integral sorry, not x, a. I just always use a, make it easier. From 0 to a of 1 over square roots of 9 minus x squared dx. I have to do my normal work here, right? I already know it's arc sine, but what do I want? I want y equals arc sine of u. I want y prime equals 1 over square roots of 1 minus u squared du, right? So I don't want the 9, right? So I'm going to divide inside by 9, which means I'm dividing outside by 3, right? The square root of 9 is 3. And it looks like I'm going to need that 1/3 as my du. So I'm going to leave it there. Sorry. So I'm doing the limit as a goes to 3 of the arc sine of x over 3 from a to 0. So it's the limit as a goes to 3 of the arc sine of a over 3 minus the arc sine of 0, right? 0 over 3. And I need the limit of the whole thing, but only a is there, so I really only need that, right? This is 0 anyway, right? Sine of 0 is 0, so arc sine of 0 is 0. And this is not bad here, right? Right? What do I get? I get the arc sine of 1, right? And when is sine equal to 1? Yep, pi over 4. Pi over 4? Pi over 2, thanks. Yeah. Crazy. Now, we didn't need our trick on that one, so what? That's fine, right? Let's do one where we need the trick. I have to find one where I need the trick. I don't know if I have one. Let me try the book. All right, let's see if I'll do 13 in the book. I think this one needs the trick. I don't remember. X e to the minus x squared. This is kind of like 13. Only I'm doing from 0 to infinity of x e to the minus x squared. So this particular graph looks like this. And of course, we're looking at this area here. We want to know if that's finite or not. So I'm going to need the limit as a goes to infinity of the integral from 0 to a of x e to the minus x squared dx. Good, get me the integral. It's a u sub. How'd you do? Anybody get there? Anybody? No one? Hello? So did you get the integral right? There's my integral. Yeah, so then I'm evaluating at a and evaluating at 0. right? For this one, I'm doing this by looking at the graph, right? I know that goes to 0. Let's do one more, and then we'll take a little break. This is from the textbook. Number 33. I've got a z squared times ln of z from 0 to 2. So x squared ln of x dx from 0 to 2. And you can see there's definitely an issue here, right? Definitely an issue with ln at 0, right? I want to get a decent picture of this. So y equals x squared ln of x So I'm going to have some negative area and some positive area, right? This is by parts. Where u is ln of x, excuse me, and dv is x squared dx. Good. Get me the integral, please. And we do. We get there? Brian? Brian? Yes? You got the integral? Anybody get the integral? Okay. Anybody get the integral? X cubed over 3 times ln of x minus x squared over 2. No one got it? You got this. You got this part. Okay. Good. So 2 of you got it. Yeah, well, I mean, you weren't here, so you got to watch the lectures and so I know the issue is at 0, right? I know the issue is at 0. Of course, ln of 0 is trouble, right? So I rewrite the 0 as a and do the limit as a goes to 0. So when I finally get down to it, there's only one piece that I need the limit for. And this is L'Hopital's rule. You remember L'Hopital's rule? So if I plug in this, what do I get? I get 0 times negative infinity, right? 0 times plus or minus infinity is an indeterminate form. So I want to put this in the form of 0 over 0 or infinity over infinity. And the way I can do that, so I'm just going to work on star here, which is minus 1/3 times the limit as a goes to infinity of a cubed ln of a. So what I do is I move my upstairs function, I move one of my functions downstairs. And the easiest one to move is the polynomial. So first of all, agreed that it's still equal? Agreed that it's still equal? Yeah, keep, change, flip, right? So now ln of 0 goes to minus infinity, and 1 over a cubed goes to infinity. So now I have L'Hopital's rule, right? Good. So derivative of upstairs is? Yep, so we're doing the derivative of ln of a over the derivative of 1 over a cubed, right? So upstairs becomes 1 over a, downstairs becomes what? Negative 3 over a to the 4th. Am I right? So I have minus a 4th over 3 times 1 over a. 1/9 times the limit of a cubed, as a goes to where? 0, not infinity, sorry. So it's 0. So the integral from 0 to 2 of x squared ln of x dx equals 8/3 ln of 2 minus 2. Right, I got that from here. How are we feeling about this? Yeah, where are we? Okay, yeah, so right here, right? We got the integral. Yep. And then we put it into our notation, right? And then we get down to, this is the last piece that we have to figure out with the limit. Say again? Yeah, because that I got a number out of that. I don't know what I'm getting out of this limit. So now I'm working on the limit, right? I see that I get a 0 times infinity. I know that's a L'Hopital's rule, but I have to have 0 over 0 or infinity over infinity, right? So so I do L'Hopital's rule, right? Simplify, and then evaluate the limit. I got 0, so I know I got that piece as my final answer. All right, let's take a little break.